Now we're going to move on from proving things about subsets to proving things about equality between sets. And just like we did with subsets, we're going to base our procedure on this formal definition of set equality. So you remember when we talked about this previously, we had this for our original definition. Two sets are equal if and only if x is an element of one, if and only if x is an element of the second. And then we went on from there and said, okay, look, that is equivalent to this statement about subsets. And this is the version that we're going to actually use to prove things. So our proofs showing equality between sets are going to have literally two parts. First, we're going to show the set on the left is a subset of the set on the right. That's this part. Then we're going to show the reverse. Then we're going to show the set on the right is a subset of the set on the left. That's this part here, right? If the first and the second subset statement are true, then that is equivalent to showing that the two sets are equal. That's going to be our goal. So I've got an example here, and I want to show that these two sets are equal to each other. And kind of notice what's going on here, right? I have this A that's outside, and over here, I combined the A with the B and got this part. And then I combined the A with the C and got this part. So what we're kind of showing here is a version of a distributive property for sets. So to do that, I'm going to use the procedure that we talked about on the last slide. And I'm actually going to do this on two slides here. I'm going to do the first subset on this one. It's going to take a little bit of room. So then I'm going to go and do the second subset statement on the next slide. All right, so what do I need to show? I need to show first A union B intersection C is a subset of this expression on the right. And we're going to follow a very, very familiar process for this. I'm going to say let X be an element of A union B intersection C. All right, so what does this mean? Well, I'm going to apply the definition of the union of two sets. Let X be an element of this union, so by the definition of union, either X is an element of A or X is an element of the intersection. It has to be in one of those, at least one of those two sets. All right, well, let's follow the implications of this then, right? If X is an element of A, then X is an element of the union of A and B, and X is an element of the union of A and C. That's the definition of union. If X is in one of those sets, then it's in the union. Therefore, by the definition of intersection, X is an element of the intersection of these two sets. If it's in both of them, then it's in the intersection. Therefore, the set on the left, therefore this set is a subset of this set. And that's what we needed to show, right? That's what we were aiming for up here. Therefore, therefore A union B intersection C is a subset of that big complicated one, A union B intersection A union C. All right, that was one case, right? If X is an element of A, good, there you go, we're squared away. Right, now let's look at the other side, right? If X is an element of the intersection of B and C, then X X is an element of B, and X is an element of C. It must be in both of them. Therefore, X is an element of the union of A and B, right? That's what this tells us. And X is an element of the union of A and C. That's what this part tells us. So again, therefore, by the definition of intersection, we have A union B intersection C is a subset of A union B intersection A union C. So that's what I needed to show, right? Regardless of which case was true up here, we ended up with the subset that we needed. That's half of the proof, right? That's half of the proof. Now we need to do the other way. All right, so let me clean that up, get us some space to work with. Now I need to show give me a little more room here. A union B intersection A union C is a subset of A union B intersection C. Now I'm going this way. Make sure I wrote that correctly. Yes. Okay, so gonna follow the same approach. Right, gonna follow exactly the same approach. Let X be an element of A union B intersection A union C. Then, by the definition of intersection, again, X is an element of A union B, and X is an element of A union C. Has to be in both of them in this case. So if think about this part here. This is saying, therefore, by the definition of union, X is an element of A, or X is an element of B. All right, well, if X is an element of A, then we're done. If X is an element of A, then X is an element of A union B intersection C, and we have, I'm not going to write that thing out again, we have the subset relationship that we needed. Okay, what if X is not in A? All right, well, if X is not an element of A, then X must be an element of B, right? Because one of these two things over here has to be true. Well, if it's not this one, then it must be this one, right? So if X, sorry, I lost the not. If X is not an element of A, then X must be in B. Also, because X is an element of the union of A and C, and again, X is not an element of A, then X must be an element of C. Okay, but wait. X is an element of B, and X is an element of C. Therefore, by the definition of intersection, X is an element of the intersection of B and C, so X is an element of A union B intersection C, which again proves the subset relationship that we needed. So we again have the required subset, and we're done. Right? This covered all of the cases. So let's look at this one again in a little more detail, right? Because I know there was a lot going on here. So I started by looking at there we go. I started by looking at this. At that point, I was just applying the definition of the intersection of these two sets. Then I said, okay, look, I've got some possibilities. This means either X is an element of A or X is not an element of A. Well, if X is an element of A, then we were done. If X was not an element of A, then I'm running out of colors. Then this forced X to be an element of B, and this forced X to be an element of C. Therefore, X must be in, left of the element, X must be in the intersection of B and C. And if X was in the intersection of B and C, then it had to be in that union. It's very high level. That's what we showed. So I have another example here for us to look at, and hopefully there's some familiarity here. Right? You see, I'm calling this De Morgan's law, and we've already seen two things called De Morgan's law back when we were talking about propositional statements. Right? And the propositional version said the negation of A or B is equal to the negation of A and the negation of B. So if you're seeing a lot of structural similarities here, that's not a coincidence. In fact, on the last slide there were a couple of times when my handwriting got a little sketchy. I had to catch myself. My U's kind of started to look like V's a little bit. Yeah, this is not a coincidence. There are some very strong ties between mathematical logic and set theory. Right? So yes, some strong connections here. But okay, let's set the logic version aside here and see if we can prove the set theory version. We're going to do this exactly the same way we did the previous ones, right? This is really going to be two proofs here. First, I need to show the complement of the union is a subset of the intersection of the complements. So I'm going to start off very familiar. Let X be an element of the complement of the union. Therefore, X is not an element of A union B. Therefore, X is not an element of A, and X is not an element of B. If it's not in the union, then it's not in either of them. Well, if X is not an element of A, then X is an element of the complement of A. And if X is not an element of B, then X is an element of the complement of B. And again, a definition of intersection. If X is in both of those sets, then it's in their intersection. That's what I needed to show. Right? I've shown that if X is in this set, then it must by necessity be an element of that set. So A union B complement is a subset of A complement intersection B complement. There's the first half. Now we got to go the other way. Now I have to show A complement intersection B complement is a subset of the complement of the unions. Very similar approach. Let X be an element of A complement intersection B complement. Therefore, X is an element of A complement and X is an element of B complement. It has to be in both of them. Therefore, X is not an element of A and X is not an element of B. Therefore, again, X is not an element of their union. Well, if X is not in that set, then it must be in the complement of that set. And again, that's what I needed to show. If X is in this set, then it must, by necessity, also be an element of this set. So A complement intersection B complement is a subset of the complement of the unions, and therefore we have shown both directions, right? Therefore, the two sets are actually equal to each other. And that's what I needed to show. All right, so I've added a second version of this. Just like there are two De Morgan's laws for logic, there are two De Morgan's laws for set theory. And you notice they both follow that exact same principle, right? The complement kind of gets distributed out to the two individual sets, and the symbol in the middle switches from union to intersection or intersection to union. I'm not going to prove this second one here. I'm actually going to leave that for the exercises if you're following along on the website. There are a lot of these. There are a lot of these set equalities, set properties. If you're following along on the website, there's a link to a page in our resources area that has a big list of them. If you're watching this on YouTube, you can find the same link down in the description. So now we've seen several examples of set identities, a distributive law in the first example, then two variations of De Morgan's laws. But there are a lot of these set identities, and we're going to cover some more of them in the exercises if you're following along on the website. And there's a link at the bottom of the lectures page that will take you to a list of them in our references resources area. If you're watching this on YouTube, then there's a link to that page in the video's description. Now, the method that we've been using, where we start by taking an arbitrary element from one set and showing that it has to be in another set, is a great tool for demonstrating these relationships. But there are situations where it can be problematic. When we're trying to prove things involving the empty set, it's a little questionable to start a proof with let X be an element of a set when you know that set doesn't actually have any elements. So in the next lecture, we're going to focus specifically on proofs involving the empty set so you can see how we deal with this kind of situation.